Okay, let's start. Can somebody just post on the group that we started so Amelia can come up? Okay. Let's start. So yesterday I gave you a question to do. So the 24.2 question 1. Did everybody do it?
We started, but
Got stuck? Which part you got stuck at? Calculating the limits. That first part you should have done it
That was easy one.
Yeah.
with no issues, right? The second part you can give you.
Because it gave me the numbers here. Negative, positive.
yes, it was also confusing.
Okay, let's do it. So, A, they ask you to calculate the magnitude of your support A and B, your RA and RB, right? So, looking at this, okay, we have two concentrated loads, one of 30 kilonewtons and one of 20 kilonewtons, right? And we have a uniformly distributed load of 15 kilonewtons per meter. Okay, that's its magnitude. Normally we multiply it by its distance to give us a concentrated load. Okay? They don't give you a weight, they don't give you a gravity, so you can disregard that, right? You have two supports. One support is 1 meter from the left, the other support is 1 meter from the right. Full length of this beam is 8 meters. Everybody's okay with that?
Yeah.
Okay. So let's start, right? So we'll say take the moments about, so for this purpose of the diagram, C is on this end and G is on that end, right? And you need to get used to something like that because won't always be A and B, right? And that happens a lot. Like, you know, in a question you solve for X, and if you change X to B, exact same method, it's just wherever you add X, you add B, but people act like they never saw it before, right? So, get used to this, right? So now we're going to take moments about C, and when we do that, we say clockwise moments is equal to anti-clockwise moments. So now if we're looking at C, right, what would cause the other end to move in a clockwise direction? Is it your upwards or downwards force? Downwards force, right? So this would now become 30 times, how far away is 30 from C? 0, right? Plus, now this uniformly distributed load, we need to convert it into a concentrated load. So a concentrated load would be, okay, let me write the, right? So this would be at the midpoint, and this would be 15 times 5. Yes? Because from here to here it's 2.5, so the remaining distance would be, yeah, well, the full distance would be 5, or you could have said this entire beam is 8 meters. There's 1 meter here, plus 2, which is 3. 8 minus 3 is 5 meters, okay? So this would be 15 times 5, which would give you 75 kilonewtons, okay? So this now would be 75, and how far away is that from C? 2.5 meters, right? Plus 20 kilonewtons, and how far away is that from C? 5. Equal to, if down caused a clockwise motion, up would cause a anti-clockwise motion. So it will be RA times 1 plus RB times how much? 7. Okay, so if you put this whole thing in your calculator, what you get?
All A is equal to 287.5 minus 7 RB.
287.5.
Yeah.
And this is equal to RA plus 7 RB. So you make something the subject of the formula, you're going to end up with 287.5 minus RA is equal to,
RB.
so take the RB across, it will be 7 RB is equal to RA. So now we got one equation. Right? Can we do anything further than that?
No.
We don't have enough information. So we'll take the moments about G.
Okay.
Same story like how we did this. Clockwise moments is equal to anti-clockwise moments. Anti-clockwise moments, right? So now we're looking at G. what would cause the other end to move in a clockwise direction? Is it your upwards or downwards forces? Don't take it down now, give your time to take it down.
Upward.
It'll be your upwards, right? So our upwards forces are RA and RB. So it'll be RA. How far away is RA from G?
7.
7. Plus RB, and how far away is that from G? 1. Equal to the first force, which is 30 kilonewtons, multiplied by 8, plus 75 multiplied by.
5.5.
You understand why it's 5.5?
Repeat that.
What is the distance of the uniformly distributed load? You know we convert it to concentrated. What is that force's distance from G? It will be 5.5 because remember this end is also 2.5. So 8 minus 2.5 will give you that remaining distance, which would be
5.5.
5.5 plus 20 kilonewtons, and how far away is that from G? 3 meters. Okay, so you end up with 7 RA plus RB is equal to
712.5.
712.5. So then you can say RB is equal to 712.5 minus 7 RA. So now we got 2 equations, right? This is equation 1. This is equation 2. So you would say substitute equation 2 into equation 1. So you're going to end up with RB equaling 712.5 minus 7 into RA, which is 287.5 minus 7 RB. So far, are we all okay? Everybody know that, right? This will be equal to 712.5 minus 7 times that
2012.5.
plus 49 RB. Right? So you'll take this across, it will become minus 48 RB equal to, and what's this number?
1,300.
1000
Minus 1,300.
on there. Okay, RB is equal to 1300 all over negative
Minus.
Of negative, yeah.
negative 48. So RB is equal to
27.083.
kilonewtons, right? Everybody understands what I did? Is anybody confused? Right? So then you'll say therefore RA is equal to 287.5 minus 7 times 27.083, and the RA is equal to
97.9.
okay. If you do your test quickly, upwards forces must equal to downwards forces. So 27.083 plus 97.900 is
125.
what?
125.
Like if you round it up, it will be 125 on the right? And if you get 30 plus 75 is 105 plus 20 is 125. So now your upwards forces is equal to your downwards forces. Everybody okay with that? Right? So that's straightforward, right? So I'm gonna write down what our force values are here. This is 97.900. This here is 27.083 kilonewtons. Okay, this is normal what we did before. Now the next question they ask you is calculate the bending moments at C, D, E, F, R, B and G. Okay, so point D is actually where RA is, right? I don't know why they never label this, but that's fine. So bending moments, right? Let me write here. Okay, so when I say bending moments, if we're looking at a point, which side would we look at? Say, so you look at to the left of a point. What would you take your clockwise moments? Would you take it as will be a positive value, your anti-clockwise moments will be a negative. So instantly, what would happen? Your upwards values will be positive and your down values will be negative. Good.
Yeah.
Okay. So now the bending moments at point C. Is there anything to the left of point C?
No.
No. So this would be 0 kilonewtons per meter. Bending moments at point D would be what?
C.
It's 30.
That's it. Minus that's it.
So that would be, so we have, okay, say like I said yesterday, right? We're looking at point D, right? How many forces are to the left of it?
One.
One. And is the force acting up or down?
Down.
Down. Downwards forces are
Negative.
negative. So the number you would have here is negative 30. And how far away is that from point D? 1 meter. So this would be equal to negative 30 kilonewtons per meter. Is everybody okay with that?
Yeah.
Who's confused?
What was the force of
Say it.
the force of the actual
What did we leave out? What you call it?
constraint the load force?
The
Downward?
uniform.
The uniformly distributed load.
Yeah.
We left out that, see when you're looking at this beam, right? Remember, let me take this out, right? This uniformly distributed load, if we're looking at point D, it also has the small portion of uniformly distributed load. Yes? And that will also apply a downwards force. So you can't just disregard it. So what you would have had to do was, you would have had to work out what the force is being applied at 1 meter. So you convert the small portion into a concentrated load, like how we would do for this entire portion. And how you would do that, you would say 15 times 1 meter, which would be 15 kilonewtons. Yes?
Yeah.
And how far away is that from point D?
0.5.
0.5 meters. Do we understand that? Is anybody confused about what I just did? Can I understand?
Yes.
That may answer. Okay. Okay, but try watch the recording, right? And then tomorrow, not tomorrow, Saturday in class, right?
Javed, what if they didn't give you that 15 kilonewtons per meter, and they just gave you the
Force.
forces, he's saying it was 75
The force being applied.
Yeah.
Yeah. But they gave you the length of the beam.
beam, yeah.
Yeah.
So what will be
You have to work that out. You'll
You
have
have
to
to
say 75 divided by 5. The magnitude of that beam, the magnitude it applies to the.
yeah.
Then from there you work out your portion for the calculator. Okay? It's just same thing but you're working backwards. So this here now would become what? Now ask the question again now. If you're looking at point D, how many forces are to the left of point D?
So
2. Is forces up or down?
down.
So those forces will be
Negative.
negative. So the first one will be minus 30, and how far away is it from point D? 1 meter. Plus your next negative force, which is negative 15. And how far away is that from point D? 0.5. So this answer now becomes
Minus 37.5.
minus 37.5 kilonewtons per meter. Do you understand what I did?
And then you are saying 15 now, minus 15, where is minus 15?
Cindy, I feel like you never listened to me this first part. See, right? So, say this was your beam, right? Same thing as there, I'm just showing it here without all the other stuff, right? And if this was the entire length of this beam, the uniformly distributed load, this was 5 meters, right? And they tell you it has a magnitude of 15 kilonewtons per meter.
Which we converted.
Normally, for the entire length of the distributed load, we get an average value of it, which is how we convert it into a concentrated load. We'll take this, multiply by the full length, right? But now you see you have the support that's acting here.
Yes.
And remember I told you when you do the bending moments, you do bending moments for all the points where force will act on it, whether it's an upwards force or a downwards force. So they call that point here D, right? Now, there's one force acting down here of 30 kilonewtons. remember something. Now ignore this whole thing. Right? This is still a uniformly distributed load that's acting there. So obviously there would be a force that's being pushed down. Right? And remember this here is 1 meter. So now what's the length of your uniformly distributed load?
It's 1.
It's 1 meter, right? It's that portion there. So to work out the force and convert it into a concentrated load, you would have said 1 times 15 kilonewtons per meter. Because remember, for the 5 meters, you would have said 15 times 5, which gave you 75, but that was for the full length of it. Now if there's only 1 meter of it, to convert it into a concentrated load, you would have had to say 15 times 1. You understand that? Okay. And its length will be at the middle of the distributed load. I mean, its force would be at the middle of the distributed load. So the length of it would be 0.5 meters. Do you understand?
Okay.
Are you sure? You understand?
One can switch.
I was sleeping.
At 7 o'clock.
It was 8
You're not supposed to follow
9 o'clock.
the lecture.
What did he say yesterday, guys? You can call me anytime at
I know, but yesterday I wasn't feeling well, man, in the night. That's why I never answered. I went to nose early. Okay. You understand it?
Yeah.
You sure?
Yeah, I can see.
Yeah, I couldn't
Okay.
figure it out.
So that's how I got it. Minus 15 because it's a downward force. And the length of it from point D is 0.5. So I multiply it by 0.5. Okay? So that's it. Right? Then we're looking at, after D, we're looking at point E. Now, point E is basically the midpoint of the uniformly distributed load. Yes?
Yeah.
Okay. So, bending moment at point E would be equal to. Now,
See, that's how, sorry man, now that also not confused us, but made us think, because the
Usually
this is at the bottom, normally we got
yeah,
it
at the top. That's why
So we have
you
to figure
redraw
out
it. You redraw it
that
like
it
how
goes
I did.
right through.
Right? So, okay, I'm gonna take out
I left
this
it like
15,
that.
right? I'm gonna take out the 15. You'll all understand how we got 15 there.
Yeah.
Okay? So I'm gonna take out 15 now. And now I'm looking at point E, right? Now point E is everything. Now I'm looking to the left of point E. Now it's everything to the left of that, right? So let's start with it now. How many forces are acting on point E or to the left of point E?
3.
3 forces. Why is it 3? Oh, which are the 3?
The D, I mean,
RA acting up,
30 kilometers.
the 30 acting down, and then the 2.5 meters of the uniformly distributed load. So now you will have to convert this 2.5 meters into a concentrated load. And you would have said, so it will act at the middle here. This distance from here to E would be what?
1.5.
1.5.
It will be 1.25, because remember, when you convert a uniformly distributed load into a concentrated load, that force acts at the midpoint of the uniformly distributed load. So it's basically half of what the entire load is. So now the entire load is 2.5. Yes? Yeah. So here you would have said 2.5 times 15, which is 37.5
37.5. Yeah.
kilonewtons. So now when you come to your calculation, the first force that acts downwards is the negative 30, right? How far away is that from point E? 2.5 meters, right? Plus your RA acts up, which is 97.900. And how far away is that from E?
1.25.
1.5. See? Point E, right? Point E, from point C to point E is 2.5. 2.5 minus this 1 meter will give you this distance, which would be 1.5. So from point D to point E is 1.5. Okay? The last force you have there is that force that's acting downwards. So you would say negative 37.5 multiplied by 1.25. which is equal to
25 kilonewtons.
on the dot. On the dot. 25 on it.
Just choose mine as the model answer then.
I know. I know. You did, and I saw you did it. I knew you never do it.
What do you mean? No, I did myself.
Don't lie.
Bruh, see how many times I wrote it out, bruh? Myself. That's why I was trying to call you.
I was thinking, sorry. Right. Do you understand what I did there?
Yes.
You can see it now.
And I need you to communicate with me. I
But
understand.
yours might be slightly off, like
Decimals.
decimals, yeah.
Okay, well, what's the number?
24.975.
Yeah. I got 25, but it also depends what you carried for.
24.975.
So you carried 97.9, I carried,
98.
yeah, I used 97.916.
Yeah,
So,
that's okay.
Where's my answers out of the? Let's see what it is.
The signs.
We put minus 30.
How about minus 30?
Yeah,
And
minus
you put minus 37.5. Yeah. Okay? So, guys, we all understand
Thank you.
that, right? So, can I take this out now? This part.
just, sorry man, I just want to go back, right?
Yeah.
I think also for the other guys as well. See that, that 37.5.
Yeah.
Maybe explain how you calculated it again.
Okay.
Right?
So, okay, I'm gonna do it like our
Yeah,
last
please.
one, right?
Yeah.
So, remember this is your beam, right? Okay, you have that uniformly distributed load, and that load is 5 meters. We know that, right? At point E, they're basically telling you that point E is at the middle of that uniformly distributed load. Yes? So, this length here would be what? 2.5 meters. Okay? Now I'm going to add the other forces that they showed here. They got a force of 30 kilonewtons. You got your upwards force of your RA, which is 97. This length here is 1 meter. And you notice I'm doing everything to the left of it because that's how we do our movements. Right? So I'm only showing the forces that's on the left of it. So this remaining distance here would be 1.5 meters. Right. Now remember, this is a uniformly distributed load. So now when we're looking at the forces that act to the left of it, it will be this downwards force, this upwards force. But remember, the uniformly distributed load will also create a force downwards. Right? So this will also create a force downwards. So I'm going to remove this part here. So now you can see what we have. Right? When we convert the uniformly distributed load into a concentrated load, you take that magnitude that they give us and you multiply it by the distance of that uniformly distributed load. So this here would be 15 times 2.5, which is equal to 37.5 kilonewtons, right? And this distance from here to here will be how much? Right? Because it will be half of the full length of that load. So this would be 1.25 meters, right? So then when you come into your bending moments, downwards forces are negative, upwards forces are positive. So this downwards force would be minus 30 multiplied by its distance from here to E is 2.5 meters, right? Plus 97.900, which is your upwards force, its distance from there to E is 1.5 meters. Plus this negative 37.5 because the force acts downwards. And its distance from there to E is 1.25. And that's how you get the bending moment at point E. Are we clear?
Hey, this is how great.
It's not bad.
You just have to break it down.
Yeah.
Yeah, it's a matter of breaking down.
Even if you're sitting in your paper and you do this, just block out the whole part and look at it again. You'll see it. Right? Don't forget the uniformly distributed load that's throughout it. Okay? So okay. Can I take this part out? Okay. I don't want you all to get confused with the old forces that's there. Okay, so that was point E. So after point E, we're looking at point F. Right? So bending moment at point F. How many forces act on point F?
1, 2, 3, 4, 4.
On F4,
1,
3.
3.
3. This, you don't count the force that actually is at that point, because when you're doing the distance part, it's going to be 20 times 0, which is 0, so you don't have to consider that. This uniformly distributed load, now because it's the full length of that distributed load, we can do our normal calculation of 15 times 5, which is 75 kilonewtons, and that distance from there to there would be 2.5. That's our normal. Right? For these ones here, we broke up the uniformly distributed load into a smaller part because that was the amount that was on your left. Did the calculation as normal, converted since concentrated load, halved its distance, that was how far away it is from point D or point E. You'll understand that? You'll need to go home and practice this again, right? So now, we have 3 forces that's to the left of point F. Yes? How many forces are up? How many forces are down?
1 is up.
1 is up, 2 is down. So let's start in the extreme left. Your first force is the downwards force, so it will be negative 30, and its distance from point F is what? 5 meters. You understand by 5 meters, right? Okay. Plus the upwards force of 97.900, and its distance from point F? 4 meters. Plus the uniformly distributed load force, which would be negative 75, and what's its distance from point F?
It's 2.5.
2.5, right? So your answer here is
4.5.
that's all.
54.164.
Okay, just 15. You can put in the calculator first, right? After F, they want the bending moment at RB. RB will basically be at that point there. Okay? So your bending moment at RB would be equal to, right? How many forces are to the left of RB?
5. 4 forces.
4 forces, right? Your R is support that's acting up, your 30 kilonewtons, your 75, and your 20 kilonewtons. Yes?
Yes.
Yes. Right? So your first downwards force, negative 30, is how far away from RB? 7 meters, right? The 1 plus the 6, right? 7 meters. Plus your upwards force of 97.900, how far away is that from RB? 6 meters, right? Plus your downwards force of that uniformly distributed load, which is negative 75, multiplied by what's its distance from RB? 4.5. Plus the negative force of the 20 kilonewtons, or the downwards force of 20 kilonewtons, how far away is that from RB? So what's his answer?
0.
Should come to
0.004. Yeah.
0. What you?
I don't know. I didn't do RB. I didn't see that I did went to G.
Okay, but this one here should also come to
0.
0.
Why?
Because see at the point where you have your support coming up, it basically brings the system back into equilibrium.
Oh.
So when it brings it into equilibrium, your upwards force will equal your downwards force, and that will make it 0.
Hence, G will also be 0.
G will also be 0 because there's no forces that's acting after that. Okay?
Okay.
So this would be 0 kilonewtons per meter, and bending moment at G would also be equal to 0 kilonewtons per meter. Right? Are we okay with it? When you check it out, you can touch it, right? Take this down because I need to do C. The C is B.
Let's start with the graph.
I'm just gonna pause the video.
That's fine.
I've paused it and now we're taking it now.
How's the Java?
I missed the whole
Sorry about that.
you missed the whole part.
Sorry, Java.
Okay. So because I don't know if there's ever going to be a situation where there's no support under the uniform distribution load. So every time there's a support or a force acting up on the distribution
Or
load,
down.
there's always going to be a force
Or
in
down.
reverse acting down on it.
Okay, so see, if you have, this is your beam, right? And this is the uniformly distributed load that activates.
Yeah.
Okay? When you, if there's a spot that's here,
Yes.
and if you join your shearing force diagram, you would basically go up, right? And then for that distance of whatever force, you basically do that. Yes? Right. Now, you have a beam, you have a uniformly distributed load, you have your support here. So your bending moment diagram now, remember, this here is a downwards force. Yes? You can't not show it in your diagram. So when you're starting a diagram, you're obviously going to start with a negative force because it's going to be pushing it down. You understand what I'm saying? You understand? Right? So you're going to have to show that on the diagram. But with the introduction of the support, which is a concentrated load, and concentrated loads are vertical lines, you're going to have to basically cut this portion. So you basically ignore the rest of the distributed load. You'll work out that force, you'll show it. For the, when you come onto the other side, so this here would create maybe some sort of form of support. When you come onto this side, you would cut the load again. And you would do your calculation again. If you had another case where you had, this was your uniformly distributed load, and you had another force acting on top of that uniform, which concentrated load. Picture you had a book and you put, I don't know, like an apple or something on top of the book. That's also creating a force, right? And you had your support here. You're basically dividing all these things into sections. Right? I can see what I'm saying. Okay, wherever there's a force, it should have a corresponding depiction on your shearing force diagram. So, here, remember it will be a downwards force from the uniformly distributed load. So your diagram, when it starts, because it's a distributed load, it's going to start like that.
Then you got concentrated.
You got a concentrated load providing support, which will move it up positively. Distributed load is going to move it.
Slope again.
How did I miss this answer?
That should slope again, isn't it?
Right? That should slope again until this point here.
Concentrated load.
You have the introduction of the concentrated load. You have to show it. So this will now move again down. And for that remaining portion, you still have the downwards force that's acting. You would have to show that. And then however the beam goes after that, if it has a support here, it will continue in that motion for all that points until this will bring it back to 0. Do you understand what I'm saying?
So we disregard that 75 complete load.
Yeah, you know why I say disregarding that is because wherever a force acts on this, you're breaking it up into sections, right? So the first force acted here, that's its section, whatever is there, right? This upwards force acted on it, that's this middle here is its section, right? This, take it out.
So you
So
basically.
I'm just not understanding why we disregard.
Because you
the
already use a
75.
portion of that 75 in each section.
I'm basically breaking up that 75, which is why I asked you, from here to here was how much? 50, right? From here to here was 15
Oh,
kilonewtons.
yes.
And from here to here was 60 kilonewtons.
Okay.
That basically makes up that 75 for that full 5 meters. You get what I'm saying? So we never disregarded it. I broke that 75 up into
We're just not looking
Portions.
at 65 as an individual force.
acting
Like I
down
see it,
because
but
of this here. If this support wasn't here, and if this was here, you can just say it's gonna go down 75 for 5 meters. But because this force is here, it became a scenario like this. If you had another force acting down, it will become a scenario like that. You have to break it up into its section. This portion here, this downwards force, also got its section where it showed. So, if you look at it, your first downwards force came straight down. For this portion here, you have a uniformly distributed load, which we showed here. At this point here, we have an upwards force, which took it up here. For this here, we have that remaining 4 meters of uniformly distributed load, which I drew there. Then I have a downwards concentrated load, which I showed there. and then we have nothing for a while, so the line continues straight until the support brought everything back up to 0.
Okay.
Do you all understand what I'm saying? Does it answer your question? Do you understand?
Okay, I think I understand now. So we still take into account that 75 force, but because of the force acting below, like you said, that support is in the middle, it's not in the end as usual. That's what's breaking up the force on the beam. Okay, I think I get it.
Yeah, so mainly we're drawing a shearing force. Wherever there's a force, draw a line for it and divide it into sections. So like how I showed you here, this here would basically show that section. Here is basically the section here, and here is basically that section. Okay? For concentrated loads, it's a vertical line. For a distributed load, it's a slope. Okay. Then they want your bending moments. Okay, bending moment diagram. We got our values for bending moments. Right? So it's going to start at that point there. And bending moment at C is 0. Okay? Then your bending moment at D, we said is
37 minus 37.5.
then the bending moment at we worked at an E. Bending moment at E is
24.
24. So it's a positive value. It says here, right? 24.
975.
975. Then at F
54.5.
and then
0, 0.
back to 0. Who confused you? Which you confused was, huh? You confused. Who's confused?
Zama said she's still not getting it.
So she's still gonna watch the
No, but she needs to watch yesterday's lecture to
Yeah.
understand what we're doing today, right? So, bending moment diagrams, look at your loading diagram, right? So if you go back to your page 76, right? Wherever a concentrated load acts, it's basically just a point on the diagram. And then the lines between a concentrated load is a straight line, right? If you look at 76 in the bottom, bending moment diagram, concentrated load, right? You're looking at that? 76, page 76, right? If you're looking at that, can you see a loading diagram? You have an upwards force, one downwards force, one upwards force. Can we all agree that that's 3 concentrated loads? 2 concentrated loads pushing up, 1 concentrated load pushing down. So on a bending moment diagram, you would have a straight line between concentrated loads. Yes?
Yes.
And if you have a uniformly distributed load, so if you're looking at uniformly distributed load at your upwards force, so you have 2 upwards forces, and then you have your uniformly distributed load in between. That now becomes a curved line. Okay? So, when I'm drawing it from here, this line, when you're joining it here, would be a curve. Thank you. Right? So this line here would be a curve. Sorry, just don't look.
It looks
It's a
straight.
curve.
Okay.
It's a curve, right? Right? Okay? From here to this point here, curve as well, because it's a distributed load. But now it will curve. Oh,
Huh? You're on
That's right.
37.
something like that. Right? Still distributed load, so this will also be a curve. Right? From here to here, what you have?
Straight, concentrate.
2 concentrated loads. Between 2 concentrated loads on a bending moment diagram, it will be
Straight.
straight line. Do you understand?
Sloping.
It looks sloping. Yeah, well, a sloping straight line.
Yeah.
Okay? Sloping straight line.
It's easier to draw.
Yeah, it's easy to do.
This one, yeah?
And then all this here. is your bending moment diagram. Ladies and gentlemen, are we okay?
Yes.
Sure.
Yes, we are.
Does anybody hate me? Yes. It's okay. Mothers love me. I'm okay with it.
Simba is not serious.
Is that what they told you?
Yeah. Shame. Please, guys, the only thing I can tell you all is please practice answering this question, right? Don't think because we did it in class you'll know how to do it. You'll know how to do it because I'm telling you how to do it. You'll need to be able to know how to do it on your own. Right? So that's your sharing and bending. Okay, can I finish this question and then I'll give you time to take it out? Okay? So the rest of it, they ask you to calculate the magnitude of the maximum bending moment and its position. I don't know if you're going to help me on how we solve this, but okay. Yesterday, what I told you, for your maximum bending moments, what's the condition?
Cut to the graph and zero. No.
When your shearing force cuts the graph at 0. Okay, that would be your maximum bending moment. I know what you're going to ask me. This graph cuts the thing at 2 places. It cuts the 0 at line at 2 places. So, which one do you choose? Now, how you do this is right. Shearing force would basically be maximum bending would be where this beam would bend most, right? If it's under a support, is it going to bend it?
No.
No. So would you worry about this one here?
No.
No, right? Because it's under a support. The least bending will obviously occur under a support because there's something holding it up. So you'd look at the other point at which it cuts. You understand that, right? Okay. I don't know if you're going to hate me now, but okay. So, maximum bending is when your shearing diagram cuts the 0 line, right? So now how do we work out? They want to know the magnitude, the maximum bending moments and its position being its distance along the beam, right? Now, we can say that it's here. But if you come down, do we know the value of it? So what we would have to do? Calculate it. And how would we calculate it? How would you calculate it?
I catch it out. The other stuff was too much for me. I'm like, the diagram done.
Kill you. Okay. Remember yesterday, right? For QS, your shearing force. Right? How would we work it out? Now, remember, this is the line we're looking at. We want to know the magnitude of that point and we want to know its distance along the beam. So if I take this up to here, right, took it all the way up to my loading diagram. Now I'm going to show you how you do this, right? When we were working on the shearing force yesterday, how do you do it? Remember sign convention, everything to the left, all that sort of things? Y'all remember what I'm talking about?
Yes.
Guys, the answer is not on my face, it's in your textbook. Please turn the textbook back and look at where sign convention is. One more time, Charlie. Right? See at the bottom left hand side, sign convention. And then on the top right hand side of the page, next page, what page is it?
74.
So at the top of page 74, yesterday we did that, guys. Cindy, did we do that yesterday? Top of page 74. Do you remember what I did? Everything to the left of the beam, whichever forces were acting up, we took it as a positive. Whichever force was acting down, we took it as negative. You all remember that? Right? So, look at the green line. What's your forces to your left?
30.
The 30 kilonewtons, the RA, and then whatever distance this uniform distributed load is from here to the green line. Yes? For shearing forces, we only worry about forces,
Yeah.
right? So, this here would be your, so it will be negative 30, yes? Plus 97.900 plus, okay, minus, right?
75.
Minus what?
75?
Why 75? Is that green line on the end of the purple line? No. So it's not going to be 75.
7.5.
What would it be? Remember you asked me earlier, if they gave you 75, right? And they told you the beam is 5 meters, how you worked out the magnitude?
So it'll be 37.5.
75 divided by
Why are you telling me 37.5?
Be half of.
Where's the green line?
But with the green line, we don't know where it's
We
at.
don't know where it's at,
So we don't
right?
have.
We don't have a force acting down. We can't put a force because we don't know its distance. But how would you have worked out that force?
We would have divided it by the
How would you have worked out the force?
other force.
That's acting down.
Meters.
You multiply 15 by the distance, and that distance would be the position that they want, right? So you would have said minus 15, and I'm gonna call that distance y. Is that fine? I'm gonna call it anything else.
Now,
It's okay, then
unknown.
y, right? Remember, your maximum bending moment is when your shearing diagram cuts to 0, right? What would be your QS value? If this is a shearing force diagram, and we're saying that maximum will occur when your shearing force diagram cuts the 0 line, your shearing force would be 0, right? So this here is 0 equal to 67.900. I just took the 30 and subtracted from there. Minus 15. Why? Take this across. Negative 67.900 is equal to negative 15. Why? So, this value of y is equal to negative 67.900 divided by negative 15, which is
Okay, I get it.
4.5 to 5 to 7.
meters. This is your position. They want to know the magnitude of the bending moment. How would you do that?
Well, it's F. A. Which force is this?
So you work the forces times the distance on the left hand side so
Oh,
that
you take
using the
all
y
the-
now.
You do exactly like how you would do
Yeah.
a bending moment question or solving for a bending moment. You would do that. So remember this green line, guys. Please don't say it's at the end where 20 kilonewtons
Yeah,
is.
that's
It's
the-
not at the end.
That's a mistake.
It's 4.5 meters. It's 0.5 meters away from the end. So there's no way you could have used anything from there to work it out. You have to have used your shearing force equal to 0. You work out that distance, now we got the position. Now that we know the position, right? Everything to the left of this, we said, was 3 forces. Your downwards force of 30 kilonewtons, your upwards force of 97, and your uniformly distributed load acting down at 4.527 meters. So to get that force acting down, what would be
15 times 4.
15 times that? And where would that force act?
In the center of
Half of that 4.527.
2.2.
So you understand what I'm saying? Right? So that force will act down here at 15 times 4.527, which is
67.9.
kilonewtons, and its distance would be what?
45.
No.
2.264. 2.26.
2.264.
Because it's half of what the entire green, the green distance from here to the green line, the green dotted line.
Okay.
You understand what I'm saying? Okay, so now your bending moment or your M would be equal to, right? Everything to the left, which is 3 forces, right? It would be 30, and how far away is that? Or negative 30, and how far away is that from the green line? 4.527. 4.527 plus the upwards force of 97.900. How far away is that? 3.527. You understand, right? Plus negative 67.905. And how far away is that from the green line?
2.264.
Right? Okay, I'm gonna write it below, right? Plus 67.905 negative 67.905 2.264. Put that in your calculator. Please don't say half plus 1.
55.1
55?
and 7
We only have one question though. Who does this?
7
4
kilonewtons per meter. This here is your maximum bending moment. So your diagram, can you see this line is slightly higher than that? This line is slightly higher than the point. So that's where your maximum bending moment will be. Yesterday you were asking me, why can't we just look at the diagram, take it? This is reasons why you can't look at that. So that's your maximum. Question E asks you for, from the bending moment diagram, find the minimum value. So look at your bending moment diagram. What would be the minimum value?
Minus 30. No,
Minus?
minus 30.
30.
7.5.
From your bending moment diagram. Minus 37.5.
Yeah. Minus 37. You never do because you never show your.
No, I changed the.
the same.
Yeah.
Okay, so this is minus 37.5 kilonewtons per meter. Okay, I know it's a lot to take in, but now at least you'll have an understanding of the. Well,
This is our expectation of exam.
this is your expectation of, like,
Now,
to me, I'd say the hardest thing they can ask you now, right?
that's a good thing.
Would be this. Problem is, they could give you a like reverse of whatever. They could give you this diagram here and tell you get that,
Yeah.
and you, or they give you this diagram, tell you get that, or something to that effect. Or they'll give you this force, right? They'll give you this, and then you need to work out this to actually start doing your answer. But how would you do something?
Simultaneous equations, you do the normal story. You do exactly the same.
Mm-hmm.
Do it from the left hand side, right hand
So the
side.
paper you do
moments.
that.
Huh?
You do it with that paper.
Yeah, I'll follow what you said.
Mm-hmm.
And say as per Japan myself, right?
Yeah. Why you do that?
So you can just, or maybe you can start from that point and work your way up.
The upward forces must be third damage forces. Then
You know what? You make me happy.
I'm
Right?
the-
I feel so happy. Right?
That's it.
Because remember something, right? That's just the force.
Hmm.
If you look at the diagram, 1, 2, 3, 4, 5 forces acting it. You know 4 out of the 5. The rule is upwards equals downwards.
Okay.
If you know 4 out of 5, you can solve the 5th one.
Okay.
That's it, right? So it's stuff like that you need to practice on past year papers to be able to look and see what, like understand the question. Understanding the question will lead you to the quickest way to actually solve the question. But to me, I'll be honest with you, I'd say this is the hardest question because if you look at the past year papers, sometimes they give you all the supports, they give you the forces acting on it, and they tell you just draw the shearing force, then they tell you just draw the bending moment. From there, they tell you calculate the maximum bending moment, which you do that. Sometimes they'll trick you and say calculate the point of inflection. Right?
You told us that yesterday.
And yesterday I told you it's that where shearing force is 0, it'll be a maximum bending value as well. Right?
37.5.
At the lowest point of inflection. So because they said from your diagram, they never wanted you to calculate any value, you just need to look at it and show it. Never did any centroids. That's the thing, I wanted to do half of it today and do half of it next week Wednesday.
Okay, yeah.
And start with
Into Abby's.
What's your better?
Abby's almost finished with his syllabus. Yeah.
What he got? What is doing?
What?
Came out. He's almost finished his syllabus. Yeah.
Hey guys, you can take that down. Just gonna pause it while you take that down.
The balance. Balance. Yeah, we're writing
No,
the
look at the exam.
first and the first we're writing.
What? My
We're
paper is
writing chemistry.
chemistry.
Yeah.
Yeah.
Then we write chemistry first, we write maths on the 31st chemistry, first is maths, 4th is your one, and Abby's is 1 week after that.
Okay, so at least first you write maths, you said.
Write chemistry first.
No, I mean on the first.
On the first is maths.
Yes,
Yes.
write maths.
Friday?
Second, third, fourth is what day?
Yeah, we're writing on a weekday, I think. Not a Saturday.
Yeah, no, those papers will all
So
be
Monday and
weekdays.
Tuesday. So Monday we write chemistry, I think Tuesday is.
We will be.
I don't believe me, is it?
Okay. I know my paper, I don't know the rest.
Okay, we write chemistry on the 31st.
Yeah.
Then we write maths on the 1st.
Yeah.
Then we write science on the 4th of August. So there's only 2 days in between.
What
3
day
days
is
in
it?
between. What day? The 4th of August.
31st is Monday.
The 4th of August is a Friday.
So at least I can see y'all on the Wednesday and Thursday, past your papers, whatever, for Friday. Okay. Okay, I don't have much time. Much time it's too late, but let me see what's just here. Now on page 87, we're looking at centroids and center of gravity. So centroids of laminar and center of gravity solid. So what a centroid basically is, right? It's the center point of a shape on an axis. Okay? So if I had to tell you all, if this is your y-axis and this is your x-axis, right? And if I have a rectangle here and I want the coordinates of the center, right? Remember with the coordinate, you would write it as an x-intercept and you would write it as a y-intercept, yes? Okay. So if I told you that this here is 70 millimeters and this here is 50 millimeters. I record it. Yeah, you see, you'll get me shot, you. Right. What would be the coordinates of the center point of the shape?
35 millimeters and 25 millimeters.
So you would say 35 millimeters and 25 millimeters, because for a rectangle on the x-axis it will be half whatever this length is, right? So it will be half of this, which is 35 millimeters. So this is 35 millimeters, this is 35 millimeters, right? And then on your y-axis it will be half of that. This is 25 millimeters, this is 25 millimeters. So actually when you're writing it, you'll start from 0 and you move, okay? So this here is 25 and this is 35 millimeters. So your center point would be there and its location would be at 35 millimeters along your x, 25 millimeters along your y. That's the centroid. Understand? Good. So a lamina, right? A lamina is a thin plate that does not possess any thickness because laminas are of negligible thickness. Page 87. We take their volume and mass to be 0, and the center of these two-dimensional figures is called the centroid, which is what I basically just explained to you. The center of all these shapes are known as your centroid. Okay? The centroids of symmetrical figures are known. Now you may be wondering what's the point of all this here. You say, for example, you're going to build a table that's 1D. That has 1D. Right? You want to balance the top. Where would you balance it? Where would be the most stable on this table? The center point, right? Which is why they use these calculations to basically understand that imagine if there was a table that has a very, very weird shape, like if this is the shape of the table. And right? You'll have to calculate the center of that, and that will obviously be the most stable point, because that would be where we can balance itself, where its weight on the left and its weight on the right will balance each other. Right? That's why they use centroids. Now that can be used for, I don't know, whatever else you use, but the table example is a nice example, right? So, for a square, if you want to know the centroid of a square, Cindy, the work is on the book, not in my face. Page 87, right? For the square, can you see you have your y and x axis? Right? Okay, your square is on it. To get your center points, you will basically take that distance of A and half it, or divide it by 2. That will give you your x-intercept and will give you your y. Remember, a square, all sides are equal. For a rectangle, you will take half the length for your x-intercept and half the breadth for your y-intercept. For a disc or a circle, your center point will be found obviously at the radius, which is half of your diameter. For half a circle, your intercept, it will be your x-intercept will be 0, your y-intercept will be 4r all over 3 pi. These are the formulas you need to know, right? Next page. To get the x component of a triangle, you will say 1 over 3 times the base. You'll see it on the figure itself, figure 4.45.
So wait, put that one there, you're just finding out what's y.
No, and x, right? So look at figure 4.45,
What's it?
above where you look at, right? Can you see they have the x component is 1 over 3 times the base?
Oh, for both, for x and y.
X and y, it's 1 over 3 times the base, and for x, it's 1 over 3 times the base, for y, it's 1 over 3 times the height. Okay? Then they tell, so guys, you're okay with that, right? How to find the centers of these shapes, common shapes. Is that one? Cindy, your friend? But yeah, it's center points, right? It's center points, so you're seeing. I'm trying to get to the example, right? Solids. Any solid consisting of particles of mass m and weight mg. The weight mg of the solid is then built up by a great number. Okay, that's unnecessary possible. That problems they're asking you. They can basically come to a point where they want to tell you about three-dimensional shapes. So for a sphere, how you would know its center point if it's being drawn on a x and y axis. Its coordinates would be 0 at the center. Right? If it's being drawn on the x and y, it's 0. For a cube, the center of the gravity would be along the x-axis. It will be a over 2. It's basically the same things, right? For a cylinder, when they're drawing it, the circle center would be found at 0, and its y-axis would be the height over 2. Okay? For a cone, center of your circle will be found at 0, and its height would be, for its y-axis, it will be height over 4. Just make a note of all that. You'll need to go through it, right, and learn it. Okay, basically. So anything I can tell you, right? I want to move on to the part where they say the moment of an area. So, the moment of an area of a lamina is the product of the area and the perpendicular distance of its centroid from the axis of rotation. Very big words, right? But what they're basically saying is, whatever the area of that shape is, multiplied by if you're looking at your x-axis, you will take your x distance. If you're looking at your y-axis, you will take your y.
Right, this is, we're working on area now.
The moment of area.
The moment of area.
Right? So, if you look at the example that they give you, right? Not example, the figure that they give you, right? The rectangle that they're looking at is ABCO. Okay, or OABC, right? You can see that? Right. The moment of the area OABC about the y-axis is equal to your area of the moment. So your area of the moment is equal to your total area multiplied by your center point. X bar will basically be your center point. Okay? And the moment of the area OABC about the x-axis would be area of the moment is equal to A times y bar. Don't worry, that's not the important thing you need to know, right? I feel like it's unnecessary words, right?
Okay.
Therefore, the coordinates of the centroid, so this is what you need to know, okay? It's x bar being the center point of the centroid is equal to the area of the moments all over your total area, right? And for y bar, so it will be area of your moments, so I'm going to show you how that goes again, right? They tell you likewise the center of the gravity. See on the top of page 92, for our syllabus we will proceed as follows. This is what you need to know, right? X bar is equal to your area of your moments over A, right? So what that basically means, this is equal to your sum of your area multiplied by your x values all over the sum of your area. So this could be A1 times x1 plus A2 times x2 plus A3 times x3 and so on and so on and so on, all over the total area, which will be A1 plus A2 plus A3 plus etc 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 etc. Right? That will give you the centroid or the center point along your x-axis. Similarly, if you want your y bar, it will be A1 times y1 plus A2 times y2 plus A3 times y3. Is that okay? Are we understanding what I'm saying? It's just for the center point. See like how we got this here?
Yeah.
That will be a formula to use to get it. Don't say so sad, okay. Making me feel bad. How much time we got? I'm sure I can do example 4.
Yeah, 20.
Okay. It all becomes clear once you do an example. They like to use big words, unnecessary words. Becomes clear with an example, right? You can say the same thing for y, right? Y bar will be equal to the area of the moments all over area. Sum of A times y all over sum of A. Y bar is equal to A1 times y1 plus A2 times y2 plus A3, right? They give you some important formula you need to know. A rectangle is equal to length times breadth. The area of a rectangle, is equal to length times breadth. Your area of your circle is pi r squared or pi d squared over 4. Your area of your triangle is half base times height. Volume, they give you the volume of a sphere, a cone, and a cylinder. Let me start from example 4.9. Can I take this up?
Okay.
Right? You all will see now, it's easy, right? Okay, so this is your axis. Axis, right? The shape they give you, okay, that's the shape they gave you. The information that they tell you is that this is 30 millimeters. That. Calculate the coordinates of the lamina in figure 4.53. That's the information they gave you. Okay? Now, how you would do this, they basically are the center point, right? The coordinates of the center point. You would divide the shape up into shapes that are easier to work with. Right? So if this line wasn't here, remember you just got that entire thing. But now we divided it into a rectangle and a triangle because it's easier to work with. Yes? We don't know the area. There's no formula for area of that entire thing. So I'm going to call this rectangle A1 and I'm going to call this triangle A2. So how would we answer this? Let's firstly solve for the area of each shape. So A1 would be equal to, it's a rectangle. What's the formula, the area formula for rectangle? Length times breadth, which should be 40 times what's the breadth?
13.
Which is
1.